Morning, dear children. So this is continuation of last class. Last class we learned how to make ammonia by using a lab preparation and also by using Haber's process by which we prepare ammonia for commercial purpose. So that is done. Now let's see some physical properties and chemical properties of ammonia. So physical properties of ammonia: density. Vapor density of ammonia is 8.5. That means it is lighter than air. So ammonia is lighter than air. Ammonia is lighter than air. So its vapor density is 8.5 only. And solubility, if you see, it is highly soluble in water. Like that of hydrogen chloride gas, ammonia is also highly soluble in water. 1 volume of water dissolves about 702 volumes of ammonia at 20 degrees Celsius and 1 atmospheric pressure. So what is there? See, 1 volume of water, if for example if you take 1 liter of water, then 1 liter of water can dissolve 702 liters of ammonia. So it sounds really amazing that 1 liter of water, very less, 1 liter, you can imagine 1 liter bottle. Okay, a bottle whose capacity is 1 liter. That means Bisleri bottle that we purchase while traveling. So in that out of that 1 liter of water can dissolve 702 liters of ammonia, provided the temperature is 20 degrees Celsius and pressure is 1 atmospheric pressure. That means ammonia is highly soluble in water. Ammonia is highly soluble in water. Then fountain experiment. This fountain experiment is done to show that that ammonia is soluble, highly soluble in water. How much soluble ammonia is in water? That means its high solubility can be proved, can be demonstrated by using fountain experiment. So you can see here, to demonstrate the high solubility of ammonia gas in water, fountain experiment can be done. And this we have already done when I was teaching you hydrogen chloride gas, solubility of hydrogen chloride gas. So in case of solubility of hydrogen chloride gas, the fountain was red in color. Now with ammonia, the fountain will be blue in color. So let's see, the procedure, apparatus, setup, everything is same. Simply in case of hydrogen chloride gas, we will be having ammonia gas in this round bottom flask, and with this jet, water will be coming up. With this dropper, we'll be putting drops of water in this round bottom flask. So with 1 drop of water only, huge amount of ammonia gas can be dissolved. As I already said, 1 liter can one drop of water. 1 drop of water can dissolve 702 drops, if you can make, of ammonia. Okay, 702 drops of ammonia. That means 702 times it is 702 times it is soluble. Means huge amount of ammonia gas can be dissolved in a drop of water. So if that is done, then huge vacuum is created in this jar, in this round bottom flask. And since empty space, empty space is, that means it creates a very low pressure here, because whatever ammonia gas was filled in this round bottom flask is all dissolved in a drop of water, and then this is at lower pressure, and liquid always flows from higher pressure to lower pressure. So a round bottom flask filled with ammonia gas. So this is a round bottom flask filled with ammonia gas. Number 2, mouth of the flask is fitted with a rubber stopper. So this round bottom flask is fitted with rubber stopper and jet. Okay, so here are two holes, then one for jet tube and the other for a dropper containing water, and this is the straw containing red litmus solution. Okay, red litmus solution. So this is the straw containing red litmus solution. In case of hydrogen chloride gas, what was the solution? Solution was blue litmus solution. Here it is red litmus solution because ammonia is alkaline in nature. So what happen is when first of all, so after fitting this apparatus, what we do is we just press this dropper. As a result, one or two drops of water goes out, and in this drop of water huge amount of ammonia gas dissolves, and this will be means after dissolving ammonia gas, this will have nothing. That means it will create a low pressure zone here. So liquid flows from higher pressure to lower pressure with the help of this jet. Okay, with the help of this jet it goes up, and then since what is going up, red litmus solution is going up, and ammonia is alkaline in nature, so ammonia can convert red litmus into blue. So ammonia can convert red litmus into blue. As a result, we'll see blue fountain coming out. Blue fountain from it. Okay, we'll get a blue fountain. So this shows how soluble ammonia is in water. Now let's see burning of ammonia in oxygen. So how ammonia burns in oxygen? Ammonia is not a supporter of combustion. It extinguishes a burning splint and does not burn in air. That means ammonia does not support combustion. That means ammonia does not burn. Ammonia does not burn. Ammonia does not supports burning. Ammonia does not supports burning. Then ammonia does not supports burning. Rather, it can extinguishes burning splint. Okay, when you bring a burning splint, a burning matchstick, then it can extinguish burning splinter. That means it helps in extinguishing fire, and it does not burn in air. It burns in oxygen with greenish yellow flame. That means it burns in pure oxygen. Air is a mixture of gases, so it does not burn in presence of air, but it can burn in oxygen in greenish yellow flame. In greenish yellow flame it can burn. Experiment burning of ammonia in oxygen. So this is dry ammonia gas coming from here, and this is oxygen. Okay, so ammonia, I'm repeating again, ammonia do not burn in presence of air. It does not burn in air, but it burns in oxygen with greenish yellow flame. So what is the color of the flame when it burns in presence of oxygen? Greenish yellow. But it does not burn in air. Rather, it helps in extinguishing burning matchstick. So what is the reaction between ammonia gas and oxygen? Let's see here. This is the reaction. 4 molecules of ammonia combines with 3 molecules of oxygen to give 2 molecules of nitrogen gas and 6 molecules of water. So this reaction, okay, can be used to prepare nitrogen gas also. So nitrogen gas can be prepared by burning ammonia in oxygen. Then what is the procedure? What is the procedure for this burning of ammonia in oxygen? Procedure: a white glass tube is fitted with a cord carrying 2 tubes, one of which reaches just near the top and the other remains lower. You can see in the figure. Ammonia is passed through the longer tube and oxygen through the shorter tube, and a lighted match is applied. Then observation: ammonia burns with a greenish yellow flame and produces water vapors and nitrogen. It shows that ammonia contains nitrogen and hydrogen. The reaction is irreversible and strongly exothermic. So this reaction can be done to Proof that ammonia gas contains nitrogen as well as hydrogen. Why hydrogen? Because of hydrogen combines with oxygen to give water, and nitrogen gas is coming out. That means ammonia gas contains nitrogen and hydrogen. So the reaction is irreversible and is strongly exothermic. That means again ammonia can combine, means nitrogen gas can combine with water vapor to form ammonia. Okay. So the reaction is irreversible and is strongly exothermic. That means huge amount of heat is released. So mixture of ammonia and oxygen is explosive and therefore very dangerous. It is very dangerous. Then let's see catalytic oxidation of ammonia. In the presence of platinum at 800 degrees Celsius, ammonia reacts with oxygen to give nitric oxide and water vapor. So simply if we burn ammonia in oxygen, we get nitrogen gas and water vapor. But if we do catalytic oxidation of ammonia, that means using catalyst. Okay, catalytic oxidation. Simple oxidation of ammonia gives nitrogen gas and water vapor, but catalytic oxidation of ammonia gives nitric oxide and water vapor. So this is the difference. Okay. In case of simple oxidation of ammonia, we get nitrogen gas and water vapor, but here in catalytic oxidation, that means in presence of platinum, if we do this reaction, then we get nitric oxide and water vapor. So the procedure here, pass dry ammonia gas and oxygen gas through inlets. These are the inlets. So through this we are passing dry oxygen gas, and through this we are passing dry ammonia gas in this test tube. Okay, in this test tube where there is platinum. Inside the tube there is a platinum. So when this gases passes through this tube and then heat is supplied from here, then catalytic oxidation of ammonia takes place. As a result, we get water drop. This here you can see water droplets. Okay, water droplets can be seen here, and in this round bottom flask, nitric oxide combines with oxygen to give nitrogen dioxide. So we get nitric oxide. What we get? Nitric oxide. We get nitric oxide. So nitric oxide and water vapor is formed, and further if we pass oxygen in nitric oxide, we get nitrogen dioxide. If we pass nitric oxygen over nitric oxide, we get nitrogen dioxide. So this reaction is also exothermic. The combustion tube, which in the heated state emits a reddish glow. So what happens is pass dry ammonia gas and oxygen gas through inlets over heated platinum placed in the combustion tube. So that the tube that we can see here, this tube is a combustion tube, and you can see here through this dry oxygen goes, through this dry ammonia gas enters, then this is the platinum, then here is water droplet, and through this delivery tube nitric oxide gas is collected in this flask. Okay, then which in the heated state emits a reddish glow. So in this when this reaction takes place, a reddish glow will be there. Then what is the reaction that is taking place in this chamber, in this combustion tube? Ammonia gas combines with oxygen gas in presence of platinum at 800 degrees Celsius to give water plus nitric oxide, and the reaction is exothermic. Then again further nitric oxide combines with oxygen to give nitrogen dioxide, which is a brown gas. Observation: reddish brown vapors of nitrogen dioxide are seen in the flask due to the oxidation of nitric oxide. So further, since the oxygen supply is there, so further nitric oxide combines with oxygen to give nitrogen dioxide, and the reddish brown vapors of nitrogen dioxide can be seen in the flask. The platinum catalyst continues to glow even after the heating is discontinued, since the catalytic oxidation of ammonia is an exothermic reaction. So the platinum catalyst that is kept inside the combustion tube will have a reddish glow, and this reddish glow remains for longer period after discontinuing the heating, because catalytic oxidation of ammonia is an exothermic reaction. So the heat needed for reddish glow of platinum is provided by the reaction itself. So it will be continuously glowing after the heating is discontinued. It will glow because the reaction is exothermic reaction. Now, reduction of chlorine to hydrogen chloride. When chlorine reacts with ammonia, it is reduced to hydrogen chloride, which further combines with excess of ammonia and forms ammonium chloride. So when chlorine reacts with ammonia, it is reduced to hydrogen chloride. That means ammonia combines with chlorine. Ammonia combines with chlorine to form hydrogen chloride along with the nitrogen gas, which combines with excess of ammonia and forms ammonium chloride. So you can see here the reaction when ammonia is in excess. If you use excess of ammonia, then ammonia combines with chlorine to form nitrogen plus hydrogen chloride, and this hydrogen chloride further combines with ammonia to give ammonium chloride. That means if ammonia is in excess, then it reacts with chlorine to form nitrogen gas and ammonium chloride, provided ammonia is in excess. The yellowish green color of chlorine disappears and white fumes of ammonium chloride are formed. So what is the color of chlorine? Yellowish green color. So yellowish green color of chlorine disappears, so when it combines with excess of ammonia and white fumes of ammonium chlorides are formed. Then when chlorine is in excess, now this is the case when ammonia is in excess. When ammonia is in excess, then we get ammonium chloride. But when chlorine is in excess, then we get hydrogen chloride and nitrogen trichloride. So reactants are same, ammonia and chlorine, but products are different depending on the condition. When ammonia is in excess, we get ammonium chloride. When chlorine is in excess, then we get hydrogen chloride and nitrogen trichloride. So then the products are hydrogen chloride and yellow colored highly explosive liquid nitrogen trichloride. So nitrogen trichloride is highly explosive liquid that we get when we use excess of chlorine, to react with ammonia. So this reaction shows that chlorine has a great affinity for hydrogen and ammonia is a reducing agent. So why we can say ammonia is a reducing agent? Because ammonia is reducing chlorine. That means chlorine is getting hydrogen. Here you can see chlorine is getting hydrogen. So ammonia is oxidized and chlorine is reduced. As a result, ammonia is a reducing agent, and chlorine has a high affinity attraction towards hydrogen. So this can be seen here. Then reaction with acids. Ammonia being a weak base. It is a weak base. Why it is a weak base? Because it is soluble in water, and when it dissolves in water, it shows the properties of a base. That means when ammonia dissolves in water, ammonium hydroxide is formed, and when ammonium hydroxide, if you put red litmus paper in ammonium hydroxide, then red litmus paper will be turned to blue. So ammonia is a weak base which accepts protons or hydrogen ions to form ammonium ions. That means this base ammonia can accept proton H plus to form ammonium ions. It reacts with acids to form ammonium salt. Since it is basic in nature, so acid plus base gives salt plus water. So you can see here Metallic salt solution. Iron sulfate combines with ammonium hydroxide to give ammonium salt, ammonium sulfate plus metallic hydroxide. So this most of these reactions we have done in chapter 4, that is analytical chemistry, in which we learned how to analyze, okay, how to identify different metals by forming different insoluble solids while combining with ammonium hydroxide. So let's see, when iron sulfate combines with ammonium hydroxide, then ammonium salt and ferrous hydroxide is formed, and this ferrous hydroxide is dotty green in color. This is a solid insoluble substance. Downward arrow means PPT, insoluble substance, and this insoluble substance is dotty green in color. It is insoluble in excess of ammonium hydroxide. So if you pass excess of ammonium hydroxide, then also it remains insoluble. Then ferric chloride, when combined with ammonium hydroxide, it forms ammonium chloride and ferric hydroxide. And the color of precipitate of ferric hydroxide is reddish brown, and it remains insoluble in passing excess of ammonium hydroxide. Then lead nitrate, when combined with ammonium hydroxide, we get ammonium nitrate plus lead hydroxide, which has a white color. This lead hydroxide is also insoluble solid precipitate which have white color, and it is also insoluble in excess of ammonium hydroxide. Then zinc nitrate combines with ammonium hydroxide to form ammonium nitrate along with zinc hydroxide. Then copper sulfate reacts with ammonium hydroxide to give ammonium sulfate plus copper hydroxide, and again this copper hydroxide is also insoluble. It forms precipitate, pale blue precipitate. But if you pass a lot of ammonium hydroxide, if you react copper sulfate with excess of ammonium hydroxide, then you will not see this precipitate. It will be soluble in water. It will be soluble in water. Regarding all these things we have already done in chapter 4. Then ammonia gas, and this is acid. Ammonia gas and acid. What are the product we get? We get ammonia salt. We get ammonia salt, and all these reactions are combination reactions because there are two reactants and the product is only one. So ammonia gas reacts with hydrogen chloride gas to form ammonium chloride, which is a solid. Ammonia gas reacts with nitric acid to form ammonium nitrate, and ammonia gas reacts with sulfuric acid to form ammonium sulfate. Then ammonium chloride is a good example where two colorless gases react to form a white solid directly. So here gases are combining to form salt, okay, white solid. These are all white solid salts. The ammonium nitrate and ammonium chloride both show thermal dissociation reaction. So this ammonium chloride and ammonium nitrate both shows thermal dissociation. That means the reaction is irreversible. Okay, so ammonium chloride can break into ammonia and hydrogen chloride. Ammonium nitrate also can break into dinitrogen oxide and water. So this is the reaction between ammonia gas and acid, and this is the reaction. Okay, this is the reaction between different metal salts and ammonium hydroxide. Different metal salts and ammonium hydroxide. Then aqueous solution of ammonia. Ammonia is dissolved in water to form its aqueous solution, ammonium hydroxide. Ammonia plus water gives ammonium hydroxide, and ammonia hydroxide reacts with acid to form salt and water. Since it is basic in nature, base plus acid gives salt plus water. So ammonium hydroxide reacts with HCl to give ammonium chloride plus water. Ammonium hydroxide reacts with nitric acid to give ammonium nitrate plus water, and ammonium hydroxide reacts with sulfuric acid to give ammonium sulfate plus water, and this we have already done. Ammonium hydroxide reacts with soluble salts of metals to give insoluble precipitate of their respective metallic hydroxides. Except sodium and potassium, this behavior is similar to sodium hydroxide solution, and so in this regard ammonium hydroxide is similar to sodium hydroxide and potassium hydroxide because it reacts with soluble salts of metals to form insoluble precipitate of their respective metallic hydroxides. So for number 7, this is the example. This is the example for number 7. So this much for today, and with this we have finished chapter ammonia also. Thank you.